So we're going to continue with events. We had independent events that we looked at, such as the 100-year flood, and now we're going to look at what it is that the law of large numbers states. Then we'll follow it up with dependent events. So this is lecture 5. The law of large numbers states that the more data you take, the closer you get to the average, and the more data you take in the aggregate, the more it spreads out the values. Quick example, if you roll the dice, if you flip a coin 10 times and you expect half to be heads and tails, 5 of each, you can only miss by 5. If you got all 10 tails and you expected 5 tails, you missed by 5. But if you were to do it 100 times, you could miss by 50. You would expect 50 of each and 50 heads, 50 tails. But you could miss by 50. So the statement on that second part that's not as famous is that you tend to be off by a larger number of actual counted values, but the average result is going to go toward what you expect. It's also known as regression toward the mean. So this is the law of large numbers. That's the actual name of it. So no one stuck their own name on it. And it's easy to understand that what the law of large numbers says is that with more trials, we tend to close in on expectation. And that is what we would call the regression, moving in on toward the mean. And so the more you do it, the more it should come around. This is what casinos rely on, because if they have a house edge where they're expected to have a better chance of winning on each roll of the dice or spin of the wheel, then in the end it'll come back toward the average. And so if all the betting is done over and over and over again, the numbers will work out the way they should, and they'll get that edge turned into a profit. So we're going to roll one die. Remember, a die is one of 2 dice or one of several dice. The one is called a die. What's the probability that it lands on a 3? We have 6 possibilities of what it might land on, and one of them is a 3. 1, 2, 3, 4, 5, and 6, where the 3 is good, and the 1, 2, 4, 5, and 6 are not. So now, grab some of the dice, and I'm about to roll this one die. And the probability that it's going to be a 3 is 1/6. But that doesn't mean that when I roll this against the wall, 1/6 of the result is going to be a 3 and the other 5 results are also going to occur. I'm only going to get one result. So that's our probability of a single toss of a die. It turned out to be the number 6 is its face. As would happen 5 times out of 6 in expectation, that did not come up winner. Now I'm going to go with 6 dice. And this could theoretically come up with one of each if it came perfectly to expectation. So I'm going to throw them down. I'm looking for 3s, and I'm going to read to you what we got: a 1, 3, 2, 4, 5, and another 3. So it did not get a 6. It actually got 2 3s instead of the 1 that I expected. But the idea here is that when you throw more, you have a greater chance for the average to catch up. Another thing that goes with law of large numbers is, let's remember, I'm behind by a 6 and I'm ahead by a 3, and I'll try it again. Odds are against, right? Probability is against it evening out just in 2 rolls exactly to the mean. But let's see what does happen. Okay, 5, 5, 5, 4, 2, 5. Okay, you heard that time there were 4 5s. And these are all things that can happen because there is no law of small numbers that says things are going to turn out average when you do them just a little bit. What we're going to look at is the expectation. And what we do with law of large numbers will be important when you do your dice lab for a quiz grade pretty early in the semester, before exam 1. Find the expected value of the number of 3s And in this case, we'll say in 12 rolls. Now the expected value is what is the likelihood that it's going to happen, which is out of 6 dice, one of them is a 3, and how many times did you try it? So you multiply it by that, you get 12 over 6, because that's 1, and you get 2. And you see that the 3s that I actually had out there did show up twice. They had 1 too many the first time and 1 too few the second time they came around to even. This is a demonstration of the concept of the law of large numbers. This is not a law that is followed all the time, because if I rolled 1, 2, 3, 4, 5, and 6, there's no way to beat it. I can't get better by rolling more dice. But the idea is that overall, with more turns that you go to try and find data, the better likelihood is that you're going to close in on the average. So let's find the expected value of the number of 3s in 42 rolls. One-sixth of the dice times 42 tries, put a 1 under it, 42 over 6. Well, that's 7. Because what happens is, each time you roll the dice 6 times, you expect to get 1 of each. How many times is 6 in 42? 7 sets of 6. And on average, you get 7 1s, 7 2s, 7 3s, 7 4s, 7 5s, and 7 6s. That's what the expected value says. And what they're saying is you're going to be closer to having them be 7s when you roll 42 times than you are having them be 1s when you only roll it 6 times. And so I'll give you another one. If we roll a die, we can either roll the same die or roll a whole bunch of dice, but if we get this going, the number of 3s in 1,200 rolls. 1/6 of the rolls, put our 1,200 right there, over 1, turns out to be 200. If you roll 1,200 dice, the average expectation that you're going to get is 200 of each kind. The idea is you're going to come much closer to that when you do it with 1,200 dice as to how much, as a percent, you're missing the average than when you did it once. So that's what the law of large numbers says. Now, here's what would happen when I'm talking about that other part of the law of large numbers. The main thing is regression toward the mean, and that is that you're going toward 200 of each. But if you roll it 1,200 times, it would not surprise me if one of the dice was off by 7 rolls, right? Instead of being 200, it was either, say, 207, or maybe one of them was 193. That'd be that single thing you're looking for missing by 7. Well, if you rolled just, let's say you roll all 6, right? The most you can be off by expecting 1 is you might have all 6 be off by 5. And you might have 0, which will only be off by 1 too low. So as the numbers get bigger, the actual total number of rolls by which you're missing hitting perfection increases. But the percentage, the mean that you're looking for, they're coming together. The percentage of times that each one shows up should close in on expectation. So that's the law of large numbers, not to be confused with what people sometimes say, which is they're playing roulette and, oh, I haven't seen the number 27 in a long time. It's due. It's got to be due, so let me bet the house on it. Because it's so due, it's going to come up next time. That's someone thinking about what they might call the law of small numbers, which does not exist. In fact, it does have a name. That's called the gambler's fallacy, which is, I'm due for a win because I'm doing poorly. Or, I've had it come up 6 times in a row, red. It's got to come black sometime, so it's got to come next. No, each one of those is independent, which is what we're looking at. The previous roll on roulette doesn't know what it just did. It doesn't say, oh boy, I better not give him another one of that same color. It starts all over again. Rolling dice doesn't know what the previous dice have done. So they would say something like the dice have no memory. They are independent events. Okay, they don't know what's going on. So the law of large numbers tries to bring you around to what the average should be But individual or small amounts of events don't do that. That's the gambler's fallacy, like something is due because I haven't seen it for a while. So now we're going to look at dependent events. Quick explanation about bingo. E, I, N, G, and O. These go from 1 to 15. These will go from 16 to 30. These will go from the number 31 up to 45. These will go up from 46 to 60. And then the O's will pick up 61 to 75. What you have is 75 numbers in a row. In order to make it easier to locate where those numbers should show up, they said anything that's between 1 and 15 will be a B, 16 to 30 will be I, and so on down the line. So that they gave you a number of what column to look in for that number potentially showing up. If it's not in that column, you don't have it on your card, because your card has 5 numbers, or in the end position it has 4 numbers and a free space, which everybody gets right away. And you're trying to do certain things, make a straight line, fill the whole board, make an upside down T, make an L, whatever they're calling for that game. You're trying to make that happen. And as we go, we'll see that it's better if they can focus you where to look instead of having to check your whole card. Whereas, do I have a 43? 43 would be an N. You check this column, and because it's N in the blank space in the middle, you check your 4 numbers to see if you have a 43, and that makes it possible for people to play lots and lots of cards all at the same time. It's quite amazing to watch. But what I want to have us take a look at here is there's 75 numbers. Here's classic bingo. Big barrel full of numbers, 1 to 75, each having a letter to tell you which particular column to look for to speed up the process. And somebody pulls the ball out. Okay, if it's 71, it's either in your O column or it's not, but there's no way 71 is showing up anywhere else. So they call out O71. And you look for it, and as soon after they've given you enough time to decide if your card or cards has or have the 71 on it, and you mark it up, then they take that and they put it in what's looking like a giant egg carton right where the 71 goes. It's an egg carton for 75 essentially ping pong balls, and they put the 71 ball into the carton. So we're going to look at some probabilities here, and we want to find the probability that the first 3 are I's. All 3 first are I's. A very important thing I said that created a dependent event. Dependent event is a case where it's not independent. Makes sense, but what does that mean? It means what happened on the first one changes what you're going to do for the second one, because it changes what's now available to happen. So it depends what happens the first time to how this second one goes. So what we're looking at is, we're looking at 75 ping pong balls in there. And only some of them are I's. In fact, 15 of them are I's. So here's what the probability is. That's the probability that the first one is going to be an I. That does reduce when you divide by 15 to 1 out of 5. There's 5 letters equally distributed when the game starts. Now we're going to multiply by what happens on the next ball. And here's what you got to do. There are not 75 in the big barrel anymore, right? I took a ball out. Doesn't matter which ball I took out for that. We're down to 74. But we're only looking for another I here. There were 15 I's when I went in the first time, and I took 1 out of the 15, right? I went from 15 down to a smaller number because I decreased the number in the big barrel from 75 to 74. At the same time, I took the number of balls that have I as their letter from 15 down to, see if you can get it. Because if you got that one, you can set up the third one. Where the same thing happens. Now, somehow I've made it through the first one by getting an I. I go to the next one, I get another I. So now here in this big carton, I have 2 of the 15 I's are out of the big barrel. And 2 balls are out of the big barrel also. So now this is 73. Because the balls were 75 before I drew the first time, 74 before I drew the second time, and 73 before I drew the third time. But the ones that are lettered with I were 15 when I drew the first one, which I did successfully, 14 when I do the second one, which I also did successfully, and then I get 13 here. And we have to multiply those to find out what's the likelihood that would happen. So, I'm going to do it fraction by fraction. You could do 15 times 14 times 13 divided by, then you would put parentheses around 75 times 74 times 73 and get yourself some kind of fraction that would work out to the right decimal. You could do 15 times 14 times 13, then divide by 75, divide by 74, divide by 73. That'll work. What I'm going to do is take it through. Regular calculator will do this also. I'm going to go 15 divided by 75. I'm going to do equals. I want to see it. 0.2. That's what the first one is. There's a 0.2 chance that the first one is an I. And if that happens, we continue. And so now I keep what's on there, and I'm going to multiply by 14 divided by 74. And now, it took those two fractions and multiplied them together and came up with approximately 0.0378. So 0.038. So a little less than 4% that I'm going to still be alive after the first two balls are drawn. We go out and we get the third one, and I'm going to do times 13 divided by 73. And now I'll get my approximate value. Approximately, this thing is 0.006738 and some more. So if I want to do that to 4 decimal places, for example, that would be 0.006. Now the 7, when I look at the 73 doesn't look like 80 to me, it looks like 70, so I go to 70, and I would say that's the probability. But what we're looking at here is the dependence, because I didn't take the first ball that I drew out, and I said, oh, I got that I that I was looking for, and now let me put it back in the barrel, which would put this back at 75 and that back at 15. This is dependence. What you take out the first time and times thereafter does change what your probabilities are going to be the next time. I'm going to look at another probability. I like to look at the probability all 3 are 1, 3, all first 3 are the same letter. Okay, here we go. We are going to have 3. We got 75 there. And it could be anything. It doesn't say what letter it's got to be. So the first one can be anything of the 75. Now, because one ball has come out, that's at 74. Whatever letter you got on the first one, now is what the second one has to be. There were 15 of each letter before that draw. Doesn't matter which letter you took out, that one letter has got fewer now. And that's why this becomes 14. And if you get through the first 2, then you look for the third one where there's 73 balls in there, but now you've taken it from 75 that were okay to keep you in play to win. Then there were only 14 where that matched what the first one was, and that worked, so you took that out. So now that group, whatever of the letters it was, it's only got 13. You go for that. Now if you look at 75 over 75, that's a 1. Because on the first draw, it doesn't have any possibility of killing your chances of winning. So we can go 75 divided by 75 if we want, and let it represent the one that's there, perfectly 100% likely that we're okay after one draw. And now comes the next one, times 14 divided by 74. Here we're looking at, I did that one. Try that again. 1 times 14 divided by 74. And that's 0.189. Okay, so that's like 0.19, a little less than 20%, a little less than 1 in 5, because there weren't as many of those that we need as there are of each of the other 4 kinds. So yeah, that makes sense to me. But now we also have to take advantage of the 13 over 73, so times 13 divided by 73. And that comes out to approximately 0.0337. That means about 1 in 30 times. So here's the story. Bingo games come maybe in sets of 15, and they're played in the morning session, they're played in the afternoon session. And so what happens is each game's chance of having them all be the same letter on the first 3 draws is that. And as I said, there are 15 games in the morning, and there are 15 games in the evening session. So each one of these has that probability of the first three being the same letter. So what I'm going to do is I'm going to take the 0.0337, that it is the likelihood of having all three of the first be the same letter. I'm going to multiply it by 15, and that gets me through all the games in the morning. And then I'm going to get that thing times 2, because there's both a morning and afternoon session, or morning and evening session, and it gets over 1. The expected value is over 1, which means if you're there in the morning session and in the afternoon session, there's an expectation that throughout the 30 games that you sit there, on average, one time, it's going to come out where the first three letters are the same. Because a lot of people don't know that the math is working this way, so when they sit there through the day, and maybe it's the 7th morning game or whatever it is, and one time all three come out the same letter, and people are like, ooh, all three the same letter, it's fixed, it's fixed. Actually, in the course of a day, running 2 sessions of bingo, probably should have happened once a day. And the person you could ask about that would be someone who works there every day. They're like, it happens every day. And the numbers do support that idea. But people think, wow, what are the odds, or what is the probability of doing it? Yeah, it's pretty unlikely that you would say what letter it's going to be and have it be all those, but it's a lot more likely that you'd be successful at seeing the first three come out that way, and it doesn't mean that it's fixed. It's what the law of large numbers is saying should happen. It's not guaranteed to happen once a day. It could happen 3 times in one day. It might not happen for a week, but on average, that's what's going on. So this is what dependent events look like. So I want to look at if events don't overlap. A rule for probability of events when they don't overlap. We have events that are what we call mutually exclusive, or sets that are mutually exclusive, disjoint sets and mutually exclusive events. I want to put these 2 phrases up here. Mutually exclusive events create what are called, so I want to take mutually exclusive and tie that to events. What are called disjoint, meaning they don't join anywhere, sets of outcomes. They are doing the same thing. This happens when events cannot overlap. Overlap is an English word that can help you understand. An overlap is like an intersection. So when we have sets intersect is where they cross, overlap, meet. And if there is that overlap, then we do not have mutually exclusive events. We do not have disjoint sets. We have some form of intersection. And so what we're going to look for is the importance of how we can determine what are the probabilities. And what I'm going to say is that for events with no overlap, now again, that can be called disjoint sets of outcomes or mutually exclusive events, the probability of A or B, now the events A and B are the events, so that's going to be the probability of A or B, so the probability of A, and then we put a U like a union. Union is something that's in a set at least once, uses the word or. And it's going to be the following. It's going to be the probability of A plus the probability of B. But that's only if we are certain the sets do not have any overlapping occurrences. So I want to look for this. Are these mutually exclusive groups? Carpenters and musicians. And the way you prove that something is not disjoint is by finding at least one that does both. Has there ever been someone who works with wood and plays music? And if the answer is yes, they are not mutually exclusive, and there is something at the intersection. There's a place where someone does both. So that's not mutually exclusive. How about doctors and lawyers? I know a doctor and lawyer. My doctor growing up, Dr. Bob Harkins, got sued for malpractice, got very interested in the law about it, then went to law school, became a lawyer also while still practicing medicine. That one doctor alone, or that one lawyer alone if you want to call him that, and that's kind of the key. You can call him either one, proves that doctors and lawyers are not mutually exclusive. And that happens kind of frequently, that doctors become experts at the law, maybe from malpractice, and then they remain doctors and become lawyers. But usually, people say, oh, I want to be a doctor, or I want to become a lawyer. People aren't usually saying, I want to become a doctor and a lawyer. That and is important because that and is part of the intersection where they meet. What about people who have driver's licenses and people who don't have driver's licenses? Those are mutually exclusive. You can't have a driver's license and at that same time in your life not have a driver's license. One or the other, right? But it's not always stuff that it's like one and the complete opposite. Sometimes things just aren't going to occur together. So we're going to look for the intersection. And if we find an intersection, which is the overlap, is not empty, then the sets are not disjoint, and therefore the events are not mutually exclusive. So what you do is you go out looking for one thing that proves that it's not going to work, and once you do that, you're all set. So how about if I want to draw a spade or a heart? Are those disjoint? The answer is yes. Why? The spades are these blue ones, right here, flat line, and the hearts are the red ones, which are on a different line. There's nothing that's blue and red at the same time. There's nothing in the second row in its place that's at the same time in the third row in its place. That goes all the way across the deck. So if we're saying, is it a spade or a heart? What's the probability of getting a spade or a heart? I would say out of 52, I would get 13 spades. Out of 52, I would get 13 hearts, and I can go ahead and add those together, get 26 out of 52. And when it's all reduced, I can recognize perhaps that that's half the deck, because they are disjoint and they can apply this option. An 8 or a club. We're going to go looking, since the 8s are the shorter list, I'm going to go looking at the 8s and see if I can find an 8 that's a club. 8 of diamonds, 8 of hearts, 8 of spades, 8 of clubs. The 8 of clubs is both an 8 and a club. So, not disjoint. Do the 8 of clubs. I found somebody who made them have an overlap. Therefore, I can't use this rule to try and find the probability of getting an 8 or a club, because I'm either going to count when I'm going through the deck. I'm going to get all my 8s, 4 8s, and when I go back for the clubs, I'll be short one. Because the 8's already sitting, the 8 of clubs is sitting with the 4 8s. When I go through my deck and get the 13 other cards that I thought I would, I'm only going to find 12 because the 8's out already. Maybe the other way. Grab all 13 clubs and go back and try and find my 8s, but the 13 clubs are off on the side. I go back to the other cards that are remaining, there are 39 in there, and I find 8s and I go looking for them, and yeah, I do find this one, that one, that one. I find 3, but I don't find the 8 of clubs because it's already gone. It's been double counted. And And that's the deal. If you have things that are double counted, you've got to adjust for that. And then we'll have a rule that works all the time. How about drawing a face card or a diamond? The face cards are down here, Jack, Queen, and King. Okay, these 12 are face cards. But are any of them diamonds? These green 3 right there are diamonds. Actually 3 cards that are not going to be able to know where to go when they're being called. Diamonds all come over here, face cards come over here. If you're the Jack of diamonds, the Queen of diamonds, or the King of diamonds, you're kind of like, which way do I go? That's because you're in the overlap, you're in the intersection. So if I want to put that up here, face card or a diamond, that's not disjoint. We actually have 3 reasons that that's not disjoint. And among the diamonds, it could be the King, it could be the Jack, it could be the Queen that are causes that. We only need 1 reason to have things not overlap. So now, we're going to come up with something that allows us to find the likelihood of something happening, the probability of something being in one set or the other. What about if they're not disjoint? Can we work that out? In general, the probability of A or B equals the probability of A plus the probability of B, just like we had. But maybe there's overlap, stuff that got counted twice. We do want to leave one of those 2 counts in there, but we don't want to leave them both in there. And therefore, this would be called the probability of A or B is equal to the probability of A plus the probability of B, knowing that we overcounted something in some cases, minus the probability of A and B. And that gets this intersection, which is the upside down U, and tells us that's where it's both. So the probability of having it be in at least one set is the probability it's in the first set, plus the probability it's in the second set, minus the probability that it's in both sets. And you don't have to make a decision that way as to what are you going to do with stuff that's in both sets. Is it going to be an A, like with the 8 in clubs, is it just an 8 and not a club? Or is it going to be in B, is it just a club and not an 8? You don't have to tell it to do which one, you just have to account for the fact that it would normally be counted twice, and you subtract out one of those 2 by subtracting out the size of the probability when you have them both in there. So what's the probability of drawing a heart or a 7? So A, the first thing we have is the probability of it being a heart. And we're not going to reduce the fraction because out of the 52 cards in there, how many are hearts? This red row is 13. 13 hearts. How many 7s are there? That's the second thing. We look for 7 straight up by themselves. We got 4. So we're not saying this is 1 out of 4 and this is 1 out of 13. We're leaving them over the 52s. Because now we're going to go back, and out of the 52 cards, is there any card that at the same time it's being a heart, it's being a 7? At the same time it's being a heart, it's red, it's being a 7. Yeah, the 7 of hearts. So we have to take that one out. Which now they're all over 52, so I can go 13 plus 4 minus 1. And I'll get 16 over 52. And that tells me 16 of the cards will do it. I'll either get all 13 of the hearts and 3 other 7s, or I'll get all 4 of the 7s and 12 of the 13 hearts to get me to that 16 out of 52. And you can see why I don't, right now, want to reduce it to 4 over 13, because it's telling me there are 16 cards that'll do it. And if you sort out the deck, here's what will happen. Let's say you come across the 7 of hearts, so you lay out all the hearts, and then you take the 7 out of that pile, and you put it kind of just up on top of it, a little further away. So now your hearts are made up of 12 and 1. And then you go get the other 7s and you find 3 more. So you got 12 hearts that aren't the 7, 1 heart that is the 7, that gets you to 13, and 3 other 7s for 16. And that's what's going to happen is you could have said, all right, I'm going to count it here among the original 13, and I'm going to count it here among the original 4, as long as I don't count it twice by subtracting it out once. And that's what the main rule we're going to have here is That does reduce to 4/13, but 4/13 is not a really helpful number to go. So we're going to stop here, and you can see a lot of the detail of what happens on this when we get into the homework for the same stuff.